is a number. It is. And I have to make sure that the upper limit is x or a function of x. So I differentiate both sides, and all I get is this, and nothing else. Now, if this is a function of x, I would have multiplied by that function prime. But there is no need because this is 1. So the function in question, the derivative of this function, is 1 over x to the third plus x. Of course, situations can get a little more complicated. For example, let's look at 18, same page. And we have y, the integral from sine x to 1 from the square root of 1 plus t squared dt. The same question. I cannot be asked to do anything else but differentiate this function. That's the question. Well, this one needs a little bit of a prep, because the requirement is that the lower limit is a number and the upper limit can be anything. So if you remember, one of the properties of the definite integral is when I'm allowed to swap the limits of integration, but I have to change the sign in front. 1 to sine x from the square root of 1 plus t squared dt. Now I'm ready to differentiate both sides. The left-hand side is y prime, exactly what I want. The right-hand side has to have minus. Like before, I have to replace t by sine x, the square root of 1 plus sine squared x. But this time, since I don't have x, I have sine x. I have to multiply by the inner function prime, which is cosine x. And this is it. Yes, it can get slightly more complicated, like, for example, 56. Any questions for me?
Yes. So I guess I'm a little confused about, do you think you could just run back through how the sine squared x wound up underneath the quadratic?
So if I had x,
yes,
and not sine x, I would have written 1 plus x squared.
Okay.
But I have sine x. So I have to put in, instead of t, I have to put in exactly what I'm given. So when I had x, it's a function of x. Its derivative has to be a function of x. So when I differentiate, the integral and dt go away, but now t gets replaced by x. Here, I don't have x. So therefore t must be replaced by whatever I have. And it will be sine squared. So it's sine x squared, that's how I get sine squared. And now I have to differentiate. Here I differentiated, but there was 1. But now I have to differentiate by the inner function prime. This is the inner function now. X was the inner function before, but since x is 1, it's just 1. Is that somewhat better?
Yes, that's better. I think, yeah, I was just confused what happened to the t, but that makes a lot more sense now. So thank you.
Thank you. So let me choose another from the easier ones. Let's say 15. In 15 we have y equals the integral from 0 to tangent x from the square root of t plus the square root of t dt. Okay. So the same thing, it doesn't need any prep. It has a number as the lower limit, whatever as the upper limit. So what do you think, anyone? What do you think we're going to write for the derivative of this function that is given in the form of an integral for us to use the fact that differentiation and integration are inverse operations. Anyone wants to give it a shot?
Square root tangent x plus square root tangent x then yeah, I'm not sure.
The derivative of tangent, like we had here, the derivative of sine.
Okay.
Like we had here, the derivative of x, but it was 1. Is this better? Is that okay? If I had x here, I would have written the square root of x plus the square root of x, done. But it's not x. It's a function of x. So I have to multiply. First of all, I replace t by tangent, and I have to multiply by the inner function prime, which is secant squared.
Yeah, that makes more sense. I think it's just tough to wrap your head around because, well, for me at least, because we're not differentiating the part.
Right. No, because we are not differentiating the function. We are differentiating the integral.
Right. Okay. And then.
So when I would differentiate the integral, this and this go away. Because of this. So when we differentiate the left-hand side, we get g prime. But when we differentiate the right-hand side, all we get is f of x. The integral disappears. These two are always paired. They have to be together. If they disappear together. And so I differentiate the integral, and I get the function. But it's the function of x, because this is a function of x.
All right, so it's g prime of x equals f of x times x prime, sort of, is...
Yes. Yes, if you want to put it in here, times x prime.
Okay.
Or whatever we have up here. But x prime is 1, that's why we didn't put it.
Right, that makes sense, thanks.
It's the same idea with x to the third prime. It's 3x squared times x prime, but we don't write it. But when we change this into a function, it's a different story. We have 3f squared times f prime. Same thing here. When this one is anything else but x, I have to multiply it here by f prime, by that prime. Better?
Much. Yep, thank you.
Thank you. So let's take a look at one more, slightly more difficult. We don't have to go to extremes. I just want, we are applying the properties of integrals. So the integral from cosine x to sine x, and there is another property that we will apply in a minute. So 1 plus 2v dv. And you could say, what's this? Well, yes, this is different than what we looked at. All our previous examples had a constant here, not a function. So what do I do now? I can't apply the rule. I can apply the rule only when I have something like this. A number to a function of x, or whatever this is, doesn't matter, from f of t dt, or f of v dv, doesn't matter. Then I can differentiate the left-hand side, and I have f of that value of f of x times this prime. But now I'm in trouble in a way, because this is not a number. If this is not a number, I cannot apply this. This doesn't work. Well, but I know a property of the integral, of the definite integral, this one. I know that the integral from a to c is the integral from a to b plus the integral from b to c. And you can see, how does this work here? Here's my sine x right here, and here's my cosine x. And I can always find a number in between. I don't care. I'm going to write cosine x to 0. You can put any number. You can put a number a. You can just put the symbol number or whatever. It doesn't matter. As long as you start at the same point, whatever this is. Many of my students want to put 0. Put 0. From natural log 1 plus 2v dv. From natural log 1 plus 2v dv. This is now set up correctly, but this one is not. But I have a way of adjusting it. Negative. Natural log 1 plus 2v dv. Now this is ready for differentiation. You can say, yeah, it's a sum of two integrals. It doesn't matter. It can be a sum of any number of integrals. Now I can differentiate it because this is now a sum or difference, if you want to call it, it doesn't matter, of two integrals. So then y prime will be the derivative of this. Can anyone give us the derivative of that integral?
So natural log of 1 plus 2b times...
Careful.
Yeah, 2 cosine x.
Times.
So, the cosine, or negative sine x.
Excellent. Plus, now I differentiate this one. Natural log of 1 plus 2 sine x times the inner function prime, which is cosine x. So it was basically the same thing, we just needed some prep. So all I'm going to do is just multiply the two negatives and put the sign in front. Sine x natural log 1 plus 2 cosine x plus cosine x times natural log 1 plus 2 sine x. Again, we don't have to go to extremes. We can choose another if you'd like. And I want to look at an application since you are a little bit intrigued by this procedure. I'm looking for an application. I think I found one in 62 or 63. So you can see another application of part 1. Do we need another example of what we just did, or can we look at an application? Where is this used?
I think the application would work.
Okay, very good. So let's take a look at 62 on 395. I'm copying the problem first. F of x is an integral from 0 to sine x of the square root of 1 plus t squared dt. We are given g of y as being the integral from 3 to y from f of x dx. And we are asked to find g double prime of pi over 6. I'm checking whether I copied everything correctly. F of x, indeed, from 0 to sine x, that's correct. And g of y, yes, I think it's 3 to y, yes it is, f of x, and we're asked that. Okay, again, we don't need to go to extremes, but let's see what this is. Okay, so in order to find the second derivative of this, obviously I have to find what first?
First.
Right. Okay, so I'll have to start with the first derivative. So let's say g prime of y. So let's differentiate. I see that g is given in the form of an integral, and I can only differentiate, I cannot do anything else, right? So I differentiate the left hand side and I get this, and I differentiate the right hand side, and what do I get when I differentiate this side? What do you think? Just give it a shot.
Why?
So let's go back for a moment. When I differentiate a function that is given in the form of an integral, I differentiate this side, and I differentiate this side. What do I get? When I differentiate this, I get f of x. So let's go back. So when I differentiate this side, I get g prime. And when I differentiate this side, what do I get?
F of y.
That's it. So I found the first derivative. I'm happy. But what does f of y mean? Is this with y in it? If f of x is the integral from 0 to sine x, the square root, blah, 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 f of y will be sine y of the same thing. Okay. So I have the first derivative as being this. But it's not sufficient. I need to determine the second derivative. So I'm going to copy this one more time. So g prime of y is the integral from 0 to sine y over the square root of 1 plus t squared dt. And now I will differentiate again, because I need the second derivative. The left-hand side is g double prime of y. What do we get on the right-hand side? Any guess?
Square root of 1 plus sine y squared.
The square root, very good, of 1 plus sine squared y, and then
Cosine squared, or just cosine y.
excellent. Finally, I am asked to find g prime of pi over 6. G double prime of pi over 6. So this is the square root. I know that sine pi over 6 is 1/2. So this is 1 plus 1 over 4. I know that cosine pi over 6 is the square root of 3 over 2. So this is 4 plus 1, 5. The square root of 5 over 2 times the square root of 3 over 2. The square root of 15 over 4. So we applied fundamental theorem of calculus twice. Once to determine the first derivative of a function given in the form of an integral. Then we realized that if this is f of x or f of y, it doesn't matter. It's the same function. I just have to replace x by y. And then I differentiate again to get the second derivative, applying the same procedure again. So when I differentiate a function that is basically an integral, then when I differentiate it, the integral goes away. The variable gets replaced by whatever this is. But since it's not just plain y, I have to multiply by the function prime, because this is the inner function now. This is the inner, goes inside. This is the outer, and this is the inner. And the inner function has to be differentiated. like every time we apply the chain rule. And that was another example with Fundamental Theorem of Calculus Part 1. I don't know if I convinced you yet. We'll look at another problem, or is it better? Do we feel better about it?
Getting better. Yeah, I think it'll take.
Yeah, better, but I feel like I need more problems. Yeah.
We want to choose another?
I think one more.
Yes, very
couldn't
good.
hurt.
Perfect. I don't know what 63 means or wants. I've just read it. It just caught my eye. I don't know. Well, let's see if this is what we want. 63. Same page, 395. And we are told that f of 1 is 12. They say that f prime is continuous. Okay. And the integral from 1 to 4 from f prime of x dx is 17, and they're asking us to find f of 4. I don't know, that just caught my eye, but I don't know if this is exactly what we are looking for. We also have 60 or 61, if you'd like to look at. So let's see what this is asking us to do. So, the integral from 1 to 4, and then we'll choose other problems. I don't know if, again, I just copied the problem. I have never looked at it. So f prime of x dx equals 17. So what does this really mean? Forget about the 17 for a moment. What does this really mean? The integral from 1 to 4 from f prime of x dx. By definition, this must be f of x. I shouldn't put the equal symbol there. I don't want to put the equal symbol. I'm just writing the left-hand side of the equation. So, by the fundamental theorem of calculus part 2, the integral of a derivative is the function, right, evaluated between 1 and 4. This is what we've done last time, what we did last time, not today. We did not calculate any definite integral yet. So I'm asking myself, what function prime is this? Well, it's f of x. It must be. When I differentiate this, I get that. So all this piece on the left-hand side is this, by fundamental theorem of calculus part 2. And this equals 17. But also by fundamental theorem of calculus part 2, this means f of 4 minus f of 1 must equal 17. But I don't have f of 4, but I do have f of 1. So this is not what we really wanted to look at. But it's a very good example. So then f of 4 for something else, for fundamental theorem of calculus part 1. 17, we are adding 12, so it's 29. It's a very good example. This is going backwards. Not what we just did a second ago. Now I'm integrating a derivative. When I integrate a derivative, I get the function. In the previous examples, we were differentiating an integral, and I got the function. Here again, I integrate the derivative, and I get the function. Or the antiderivative, if you want to call that, which it is, also the antiderivative. Okay, I think we need to do another example. Yes, 60 or 61. Let's read the problem together and decide. I want you to decide. So f of x is blah, blah, blah. It's given in the form of an integral on 60. On what interval is f increasing? That's one possibility. Second possibility, 61. On what interval is this curve concave downward? So choose. So we did this one and this one. And I think I saw something at the very end of this chapter, something with the same property that to illustrate. Maybe, oh no, this is the end of, okay, so this is, Yeah, so I do remember seeing this. 68, find the limit. The limit of an integral. So you choose 60, 61, and 68. Which one?
I think either